All right, if you made it this far, I guess you've earned it. We now learn derivatives using the shortcut. Yes, which means that if you are using the shortcut on 9.4, then I'm going to count everything wrong. So better go back and fix it. Okay, but 9.5 is all about the shortcut. So let's go over it. So the shortcut to the derivative. The derivative, which we know as f prime of x, y prime, or dy over dx, all represent the derivative of f at x. So these three notations all represent the derivative. The first one is f prime of x, the second one is y prime, and the third one, dy over dx, is called Leibniz notation. But I mean, if you see it, just know that it means a derivative. It says, what is the derivative of y with respect to x? That's how you say it. There's also one more notation that's also as d over dx. All this says is take the derivative of whatever expression you're given with respect to x. That's how we say it. Okay. So if you see any of those notations, they mean find or take the derivative, right? All right. Rule 1 for derivatives, the constant rule. If you are given a constant, then the derivative of any constant, no matter what, will always be 0. So remember, a constant is just a number without a variable, which we have examples below. So example 1, if f of x equals 3, which is a constant, then the derivative of 3 will be 0. That's it. Nothing more to it. B, if y equals 5, then the derivative y prime will also be 0. Too easy, I know. Too easy. But then again, remember, why is it 0? Why is the derivative of a constant 0? Because remember, derivative means slope. So if I were to draw one of these functions out, let's say I draw f of x equals 3. This is the graph of y equals 3, which is a horizontal line. What is the slope of all horizontal lines? 0. Oh my goodness. That's why the derivative is always 0. Because remember, the derivative finds the slope of the original function, and the slope of that original function happens to be 0. Okay, that's it. I know. Awesome. Good visuals, right? Okay, the next rule is probably the most important rules for derivatives. It is called the power rule. The power rule. So if you're ever given any function of x to the nth power, then the derivative of that function is given by n times x to the n minus 1. So all this says is take the power down, move it in front, and subtract 1 from the original power that was there. That's it. That's all it says. So power rule is now your best friend from now on. Not before, but now. Okay. So let's go ahead and try the power rule out for these derivatives. So once again, we're learning the shortcut. We have earned it. So if we want the derivative of x to the 5th, we will say f prime of x. And the way the power rule works is the 5 comes down, and I'll do it step by step for this first one. That exponent of 5 comes down, it multiplies the x, and you subtract 1 from the exponent that was originally there, which was 5, which will give us 5x to the 4th. That's it. That's the derivative. no more f of x plus h minus f of x over h. Well, the limit of that, right? Here it is. That's a shortcut. We just did that in like 2 seconds. It's beautiful. Okay, that's how the power rule works. Let's try it again. Y equals x to the 30th. So we're going to say the derivative y prime is going to be 30x to the 29th. That's it. Nothing else to it. Couldn't be more easy, right? Calculus is easy. Now imagine doing the f of x plus h on this. You would have to distribute that out about 30 times. So this question could, the long way could take you probably like a day, maybe 2 days. Who knows? All right. Next, y equals t to the negative 3. Same thing. I'll play around with notation just to do it. So the derivative I'm going to say for this one is dy over dt. This says take the derivative of y with respect to t. And no matter what, we're still taking the derivative using the power rule. Like I said, it's just a play on notation. They all mean the derivative. So that negative 3 comes down. And I'll do this one step by step because we have a negative exponent. So you still take 1 away from the power that's there, which means we'll get negative 3t to the negative 4. All right. This is done, but let's say in case you had to rewrite it. Let's say my math lab was being really picky and wanted you to rewrite this. You would use negative exponent properties to rewrite this. So this also can be rewritten as negative 3 over t to the 4th. Just know how to rewrite these in case it asks you to. All I used for this one was that negative exponent rule of x to the negative n equals 1 over x to the n. That's all I did. So just be prepared for that if it asks you to rewrite it. Okay. And you see how all of this is purely algebraic. Just use an algebraic property to rewrite that. All right. D. So with this notation, d over dx, all this says is, hey, take the derivative of this power function or power expression with respect to x. That's it. So this becomes 5/3 x. And since it's a fraction, I'll do it step by step for you as well. You would take the original power and subtract 1, which means that this number has to be turned into a fraction. So you put it as 1 over 1 and multiply by the common denominator of 3. This will become 5/3 x, and all of this, I'll just keep doing it. Why not? Becomes 5/3 minus 3/3, and our final answer is 5/3 x to the 2/3. There you go. So D was a derivative of an expression. A, B, and C were derivatives of functions. Okay, just know that difference. All right, more to go. Let's keep going. These are fun. Too easy. All right. So for 1 over x to the 4th, we cannot take the derivative in this form, which means, again, we will rewrite it algebraically using that negative exponent rule, because we cannot take the derivative in this form yet, not until we learn something called quotient rule. So since we can't take it in this form, I will rewrite it as x to the negative 4. And once again, this uses that property of x to the negative n equals 1 over x to the n, which means now we can take the derivative of x to the negative 4. So we'll say f prime of x, that negative 4 comes down, and you get negative 4x to the negative 5th. All right. Once again, this is good, but if you have to rewrite it, this has to become negative 4 over x to the 5th. Okay. Again, y equals the square root of u. We do not know how to take the derivative in this form. So again, we must algebraically rewrite it. So the square root of u can be rewritten as u to the 1/2. And for that property, we use that the square root of, what can I say? Or actually, the nth root of x is the same as x to the 1 over n. So that's the property we are using here. Okay, which means let's continue with the derivative. Y prime is going to be 1/2 u, and when you subtract the 1, you get 1/2 minus 1, so 1/2 minus 1, which will give me negative 1/2. Now, once again, cool, but if you have to rewrite it, then we must rewrite it. So this will rewrite to 1 over 2 u to the 1/2. Which, that's fine, but also one more rewrite could be 1 over 2 square root u. And again, the reason I'm showing you how to rewrite these is 1, because it's important to know, and 2, who knows what my math lab wants, right? Picky program. All right, there's that. And again, now, again, those were derivatives of functions. Now we have the derivative of an expression. So the way to handle this is, first, we must rewrite this term, this expression, algebraically. So using all the properties we've learned so far, this becomes d over dx of 1 over x to the 1/2. And then d over dx of x to the negative 1/2. So we have went from radical to rational exponent, and then we go from positive rational exponent in the denominator, flipping it up by the properties we've learned today, by the negative exponent rule, and making it x to the negative 1/2. And the reason we do this is because it's the only form we can use the power rule on. This is why we must algebraically rewrite it so we can take the derivative of it. And since I have not taken the derivative yet, That's why this notation has to tag along, because we have not taken the derivative at all, which means the next step, we're taking the derivative. So that negative 1/2 will come down. The x will be there. And once again, you have negative 1/2 minus 1. Put 1 over 1, make that by 2 over 2. That'll give you negative 1/2 minus 2 over 2, which gives us negative 3/2. And that's the exponent that goes right there. Okay. All right. Once again, that's good. But if we have to rewrite, then this becomes negative 1 over 2x to the 3/2. And that's it. Let's hope you don't have to rewrite that one as a radical. That should be it. Okay. Okay. So that's power rule, your best friend, which we will use from here on out. All right. 3, constant multiple property. All this says is that if there is a coefficient in front of your function, move it to the side, take the derivative of that function, and then multiply that coefficient back in. That's all it says. So just like limits, if it was the limit of 5x, you could take that 5, move it to the front of the limit, apply the limit, and then multiply that 5 back in. That's all we say. So this means when we take the derivative of this function, all we're looking at is this function x squared, which means when I take the derivative, f prime of x, that 3 stays outside, and inside we have the derivative of x squared. And the derivative of x squared is just going to be 2x. And then multiply the 3 in, done. That's it. Okay, that's how the constant multiple rule works. Now, could we say that this 2 just comes down and multiplies the 3 and we're done with 6x? Yes, we can, right? It could be as easy as that. But again, just showing you how these rules work. So for b, y equals t cubed over 6. So I want to use the constant multiple rule. So I will manipulate this by taking out the coefficient. So if I want to rewrite this, this becomes 1/6 times t cubed. It's the same thing, 1/6 times t cubed. And now we're ready for the derivative. Y prime is going to be 1/6, and the derivative of t cubed is 3t squared. Multiply it back in, and you get 1/6 times 3, or 3/6, which gives me 1/2 t squared. There it is. That's it. All right. Again, manipulate this, and we will get 1/2 times 1 over x to the 4th, which requires one more manipulation or rewrite as 1/2 times x to the negative 4. So pull out the 1/2, flip the x, make it x to the negative 4, and now we are ready for the derivative, which means, again, let's do a play on notation. I'll say dy over dx. The derivative of y with respect to x, now 1/2 stays out front, and the derivative of x to the negative 4 will give me negative 4x to the negative 5. That 4 comes down, you subtract 1 from that 4, and you get negative 5. Okay, multiply that 1/2 back in. 1/2 times negative 4 is negative 2, and you get x to the negative 5. Once again, good answer, but if on the chance it makes you rewrite, then you have negative 2 over x to the 5th. All right. Awesome. And that is constant multiple property. Moving through these, right? Way too easy. Lots of algebra involved. Now calculus is easy. The only calculus you do is the power rule. The rest is algebra. Insane, I know. Okay. So force is the sum and difference properties. So all this says is that if you have multiple terms, you can apply the derivative to all those terms. That's all it says. Just like the limit properties. If you have the limit of 5 terms, you can take the limit of all 5 terms separately. Now it says if you have the derivative of 5, 6, 7, 100 terms, you can apply that derivative to all the terms separately. So that's how it works. So let's go ahead and do it. All right. So for this one, all right. F of x equals 3x squared plus 2x. All right. So all we are worried about here is the derivative of x squared and the derivative of x. So when we set up for the derivative f prime of x, the 3 stays out front. And what is the derivative of x squared? The derivative of x squared is 2x. Plus, that 2 stays out front. And now, what is the derivative of x? Ooh, that's something we haven't seen yet, right? How would you handle the derivative of x? So I'll just say d over dx of x. Okay. Well, if we're doing the power rule, we have to think of powers. So remember that x is always to the power of 1. So if you are taking the derivative of x to the first power, that 1 comes down, and you get 1x to the, and by the power rule, you always take 1 away. So it's 1 minus 1. I'll write that down below. You get 1 minus 1, which then leaves me with 1x to the 0th power, where anything to the 0th power is always 1. If you said 0, please exit and quit the class. Just kidding, but don't do that. Anything to the 0th power is always 1. So this becomes 1 times 1, which is just 1. So to make it really, really simple, all we have to do is say the derivative of x by itself. The derivative of x is always 1. That's it. The derivative of a single variable, x, t, y, whatever, is always 1. So whatever goes in this box is 1. There you go. Which means we get our final answer of f prime of x equals 6x plus 2. There it is. That's it. All right, let's do it again. Okay, so for this one, y equals 4 plus 2x cubed minus 3x to the negative 1. All right, I assume we are professionals by now, so we can put all those rules together and just make this one real fast process. So we're going to say the derivative y prime. What is the derivative of 4? 4 is a constant. The derivative of any constant is 0. Plus, there you go, 0, right? The derivative of 2x cubed, that 3 comes down, multiplies the 2, makes it 6x. You take 1 away from that power of 3 and you get 6x squared. And then the derivative of negative 3x to the negative 1, then negative 1 comes down, multiplies the negative 3, making it a positive 3x. You take 1 away from negative 1, right? You say negative 1 minus 1, and that'll give us negative 2. Oh, easy, right? And now just clean it up. And we get y prime equals 6x squared plus 3x to the negative 2. There you go. And if you had to rewrite this one, you definitely could as 3 over x squared. All right, fun. Next one. We have to do some rewriting because of, because of this term. So once again, we use that radical property, radical to rational exponent. So this will become y equals w to the 1/3 minus 3w. Remember that this uses the property of the nth root of w will be w to the 1 over n. Okay. Which means it's now in its proper form, which means we are ready for the derivative. So y prime, the derivative, is going to be 1/3 w. You got to subtract that 1, which becomes 3 over 3, which becomes w to the negative 2/3. All right. And the derivative of 3w. What is the derivative of w? It's the same as the derivative of x. A variable by itself to the power of 1 is always going to be 1. So this is going to be minus 3. That's it. And if you had to rewrite this part, that would be 1 over 3w to the 2/3 minus 3. If on the chance. Okay. And d. 5 over 3x squared minus 2 over x to the 4th plus x cubed over 9. So it has d over dx out front, which means take the derivative of this expression. So this is an expression, not a function like the other ones above it. So that d over dx has to tag along the whole way until we're ready to take the derivative. And we are not ready yet because we have to rewrite this one, and that one. We have to do a bunch of rewriting. All right. So this is going to be d over dx of, and let's go ahead and rewrite this one first. 5/3 x squared becomes 5/3. What's the best way to do it? I'll separate it. I'll say 5/3 x to the negative 2. You pull the 5/3 out, you flip the x squared up. Okay. Minus, and now we do 2 over x to the 4th. That becomes 2 out front times, take the x to the 4th, flip it up. And the last one is that x cubed over 9, which plus, take out that 1/9, and x cubed just sits right there. There you go. It has been rewritten algebraically, and now we take the derivative using power rule on all the terms I have boxed. So first starting 5/3 times the derivative of x to the negative 2. So the d over dx disappears because we're now ready for the derivative. So the derivative of x to the negative 2, negative 2x to the negative 3. Minus 2 times the derivative of x to the negative 4, negative 4x to the negative 5. Plus 1/9. Derivative of x cubed, 3x squared. There you go. Derivative is done. Calculus is done. Rest is purely algebraic from here. No more calculus involved. We're back in algebra. All right. So 5/3 times negative 2. That is negative 10/3 x to the negative 3. Okay. And then negative 2 times negative 4 x to the negative 5. That becomes positive 8x to the negative 5. And then last is 1/9 times 3x squared. That gives me 3 over 9, or 1/3 x squared. And there it is. Of course, if you needed to rewrite it, you could have negative 10 over 3x cubed plus 8 over x to the 5th plus 1/3 x squared, if you had to rewrite it. All right. Good stuff. Okay. What are we on? Oh, almost last page. All right. So we've been doing a lot of rewriting and rewriting to find the derivative. So that's what these examples are all about as well. This says rewrite before finding the derivative. So we are given f of x equals 1 plus x squared over x to the 4th. We cannot take the derivative in this form, so we have to rewrite it algebraically using algebra properties. So with that being said, let's look at the function. So it was f of x equaled 1 plus x squared over x to the fourth, right? 1 plus x squared over x to the fourth. Okay. So how do we rewrite this algebraically? Well, first thing we have to do is break up the fraction. We see that in the numerator, there are two terms over the same denominator, which means if you have multiple terms in the numerator over the same denominator, this means you can break the fraction into those multiple terms, which means that this fraction can be rewritten as 1 over x to the fourth plus x squared over x to the fourth. We have now split the fraction into two pieces, which means now we can simplify and rewrite. Rewrite some more. First off, 1 over x to the fourth becomes x to the negative fourth. Plus, over here, these are going to reduce. X squared over x to the fourth becomes 1 over x squared, which means we must rewrite it one more time as x to the negative fourth plus x to the negative 2. Big question is, have we taken the derivative yet? And that answer is no. But we have put it in the proper form to take the derivative. So now we can find the derivative of the rewrite, which is at the very end, and f prime of x, and the derivative of x to the negative 4 is going to be negative 4x to the negative 5th. And the derivative of x to the negative 2 is going to be negative 2x to the negative 3. Done, done, done. And if you need to rewrite it, well, now you know how. Okay, that's it. If it looks like something we can't take the derivative of, algebraically manipulate it until we can. One more. Same as above. We are given the derivative of 5 minus 3x plus 4x squared over x. We cannot take the derivative in that form, so we must rewrite it. So how many terms are in the numerator? There are 3 terms in the numerator over the same denominator, which means we can split this into 3 fractions. So I'll get f of x equals 5 over x minus 3x over x plus 4x squared over x. Okay. We have just broken the fraction into 3, and now we write it. The first one we rewrite is at 5 over x. That's going to give me 5x to the negative 1. And then the next one we rewrite is the 3x over x. Those x's will cancel, and you're left with minus 3. Plus 4x squared over x. This x squared and that x squared will cancel and leave me with 4x. And we are now ready to take the derivative. This function is now in proper form. So f prime of x, the derivative of 5x to the negative 1 is going to be negative 5x to the negative 2. The derivative of negative 3 is a constant. So the derivative of negative 3 is 0. And then the last part is, what's the derivative of 4x? Well, that's just going to be 4. And that is it. So rewrite as much as necessary so you can take the derivative. Find the derivative. Okay, awesome. Okay, those are derivatives. Not bad. We don't have to do the long way anymore. Which leads us to the last page now, I believe, of an actual application to derivatives. So once again, it doesn't just seem like we're crunching numbers and all that good stuff, or doing any like plug and play. Okay. So now 7, the total sales of a company in millions of dollars, t months from now, are given by the function s of t equals 0.05 t cubed plus 0.2 t squared plus 4t plus 6. Oh, find the derivative s prime of t. All right, so that's A. Okay. First up is the derivative of 0.05 t cubed. So that 3 comes down and multiplies the 0.05, which means if I have 5 cents and triple it, I get 15 cents. So that would become 0.15 t squared. Next is the derivative of 0.2 squared. Well, that 2 comes down and multiplies 0.2. So once again, if I have 20 cents and double it, I get 0.40 t. And then the derivative of 4t is just going to be 4. And the derivative of 6, the constant, will be 0, which we don't need. So there's the derivative. That is A. Now, what did I do? Oh, we're good now. 0.015 t squared, 0.040 t plus 4. Okay, excellent. So B says find s of t and s prime of t. Okay, so calculator time. So take 2 and plug it into the original function, and take 2 and plug it into the derivative. And then, well, we can probably do C as well, because it says plug in 13 to the original, plug in 13 to the derivative, and interpret what they mean. Okay, so let's just do them all together. All right, calculator time. I'll just do this. That'll work. Clear, 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 clear. All right, then let's see my function. So we'll go with regular s of t first. So that's what I'll type in first. 0.05 x cubed plus 0.2 x squared plus 4x plus 6. And on your calculator, you must use x. So just replace t with x. All right, enter, and I'll plug in 2, and I'll plug in 13. All right. S of 2 gives me 15.2, and S of 13 gives me 201.65. Okay, and now back to drawing board, back to table, and now we'll do the derivative. 0.15 x squared plus 0.4 x plus 4. 15x squared, 0.4x plus 4, enter, 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 and that 2 and 13 should be there already, making this fast. And I'll get 5.4. And for 13, I'll get 34.55. Okay, awesome. Now let's interpret what they mean. Okay, so remember the beginning, the sales are in millions of dollars and T is in months. So for the red one, for this one, after 2 months, sales are $15.2 million, right? So in 2 months, we have $15.2 million, right? But then what does the derivative mean? So I know I didn't say interpret these two, but why not interpret them if we're going to interpret C as well? This will help us interpret C. The answer is for C. So what this means is that since it's a derivative, remember that derivative is finding the slope. It's finding the rate of change, either a rate of increase or a rate of decrease. So this says that at 2 months, and what we have to look for here is the output positive or negative? That'll determine, if it's positive, it'll determine whether it's increasing. If it's negative, that means it's decreasing, because you have to think of it in slope terms. So this means that in 2 months, at the 2-month mark, our sales are increasing by $5.4 million. So sales increase by 5.4 million, which means it's going to be the same exact explanation below. So for these guys, we can say at 13 months, sales are at 201.65 million. And since this number is positive from the derivative, we can also say at 13 months, sales are increasing at $34.55 million per month. All right. So at 13 months, you have a total sales of 201.6 million. And at 13 months, your sales are increasing at $34.55 million per month. So that is your interpretation. And that is it. That is derivatives the short way. You are welcome. Just know your algebra. Watch those tiny mistakes. All right, that's it.